Welcome to the Interactive Blended Media resource. This is where we use animation to explain the scientific concepts behind ionic liquid and coronary artery stents. I suppose the first thing we need to do is link it back to the IFM research. The first topic or scientific concept that we're going to cover are metals. Linking back to the stents, as you can see on the left, we have the magnesium stent, which is going to be coated in the ionic liquid. And on the right-hand side is the stainless steel stent. This is what's currently being used. Both metals are hard, have high melting points, high densities, thermal conductivity, electrical conductivity, luster, malleability, and ductility. The following slides to come all show how physical properties of metals provide evidence of the structure. Up first is hardness. Here on the model you can see a cation and an anion there. Now the reason why metals are hard is because strong electrostatic attraction between cations and electrons, or the anion, make it difficult to separate particles from one another. The next slide, high melting temperatures. Using the same sort of model there, I'm going to point out there's a cation again, and the anion, the electron there. And now high melting temperatures. Due to strong electrostatic attractions between cations and electrons, this means that a considerable amount of heat energy is needed to move the ions out of their fixed positions. The next property is high density. What we're looking at here is see there, the cations there are tightly packed together with the little electrons sort of just touching in between. And the rationale behind it is cations are packed tightly together in an ordered array. This packing means that more ions fit into a given space than would fit if the ions were sort of randomly packed. The density depends on the mass and volume of ions and their type of packing. Moving on to the next property, thermal conductivity. Okay, so what we'll do here is look on the left there, we're just adding a heat source here. Now just watch what this heat source does to the little electrons, the yellow ones in the middle. Okay. Alrighty, so as you can see, that little electrons seem to sort of travel from left to right there. The rationale is mobile electrons absorb heat energy from a heat source. These electrons move rapidly, colliding with other electrons. Now energy is transferred between electrons and the heat is moved quickly to cooler parts of the metal, as we sort of saw as the heat source moved the electron from left to right there. The next property we're looking into is electrical conductivity. So here we have, this is like a metal rod. And on the left here, now there's 3 electrons on the left. So as you can see, the electrons are going to slowly move in towards the rod. And as you see, looks like 3 pop out on the other side. The rationale, when a metal is placed in an electric circuit, electrons enter one end of the metal, in our case the left side. The same number of electrons then exit from the other end of the metal, as we saw, 3 electrons on the right. Delocalized electrons move freely through the structure. Metal cations vibrate, causing a barrier to the smooth flow of electrons. Some energy is therefore lost, but it causes a metal to heat as a current passes through it. Which brings me to my next question. As this is an interactive inquiry, why does a metal heat up as a current passes through it? It's something to think about. The next property we're explaining is luster. So as you can see here, this orange arrow, this is imagine shining a torch or a sun ray down onto a metal. And what happens is it sort of reflects back. And the rationale, light reflected by the mobile electrons causes metal to shine. So it's just bouncing back there. Which brings us to our last property that we're going to explain, malleability and ductility. As you can see here, if I apply some force to the left here, what you'll see is that the bottom half of the metal is being sort of pushed to the right, as you can see. And the rationale for this is the bonding in metals is non-directional. This means that the particles can be moved relative to each other without sort of breaking the bonds between them. So when a force is applied to a metal, in this case sort of the bottom left-hand corner, so someone's pushing it, one layer or a couple of layers of ions can slide over one another without the bonds breaking. This allows for changes in shape of the metal to form sheets or wires, as you can see from this model here. Now, as I said, this is an interactive blended media resource, so now it's your turn. You need to use animation to explain the other scientific concepts behind ionic liquid and coronary artery stents. If you've forgotten what they are, there is an additional PowerPoint in this resource kit that will explain them to you. Otherwise, I'll help you out here. It's ionic bonding is the second concept, and surfaces or small particles is the third concept. The way I used this PowerPoint with the Slowmation animation was through digiexplanations.com.au. If you go to their site, they have tutorials and they can show you how to put together sort of a PowerPoint, blended media, Slowmation all together. Just make sure when you submit that you make sure your inquiry reflects the way scientists research and develop ideas, present chemical ideas, and define vocabulary. Good luck.